morning and welcome to session one of our data sciences conference with Temple University. And our first session this morning is very topical given the times in which we live. Our first session is leveraging COVID-19 data for quantitative investing. And monitoring and hosting today's, all of today's sessions for that matter, is going to be Edo Arioldi from Temple University, where he is the professor of statistics and director of the Fox Data Science Center, excuse me. Also joining us this morning from Yale University is Nicholas Christakis. And Nicholas at Yale is a Sterling professor and co-director of the Yale Network Science Institute. We are also very fortunate this morning to have David Madigan. David comes to us from Northeastern University, where he's provost and a professor of statistics. And also joining us, we are very fortunate to have Ben Yu. Ben comes to us from the University of California, Berkeley. Ben is a professor of statistics and a Chancellor's Distinguished Professor. We thank you all for participating this morning, and we're excited to have you. So, Ed, I'll turn to you, sir.
Thank you, John. I also want to chime in and welcome our distinguished faculty guests on behalf of the Department of Statistical Science here at Temple University. So thank you all for being here. As John mentioned, today's panel, first session is about COVID and COVID data and meta-analysis involving complex data sources. So the first speaker is going to be Nicholas Christakis. Nicholas is an expert of COVID. Back in April, he published one of the first papers tracking the epidemic in China on a journal called Nature. And he has recently published a book titled Apollo's Arrow that's been translated in 5 languages and counting on COVID. So Nicholas, welcome and thank you for being here. I'm going to turn it over to you.
Thank you very much for having me, and thank you to my fellow panelists. I'd like to spend the time that I have with you talking a little bit about some basic epidemiology about this pathogen, and summarizing some of the work we've been doing using a variety of data and statistical techniques, and then close with a little bit about what I think is likely to happen in the coming 4 years as this pandemic continues to afflict us. So something very unusual has happened to us as a species. We happen to be alive at a moment when a new worldwide pathogen has been introduced into our midst. This doesn't happen very often, maybe every 50 or 100 years. And this new virus, this SARS-CoV-2, is going to be with us forever from now on, circulating among us. And in fact, the way we have come to live in this time, in our time in the pandemic, may feel, it probably surely does feel, very alien and unnatural to us. But it is actually neither of those things. Plagues have always been a part of the human experience. What's happening to us right now is not new to our species. It's just new to us. We think this is so unusual, so weird, so intolerable in a way, but actually our ancestors have been dealing with plagues for hundreds or even thousands of years. And by this time in the course of the epidemic, 9 or 10 months into the pandemic, we know quite a bit about this pathogen. We know, for example, how lethal is the pathogen. A recent sophisticated meta-analysis of many studies has revealed that the infection fatality rate of this pathogen is between 0.5 and 0.8%. And actually, if you develop symptoms of the pathogen, because only about half the people develop symptoms, you have to double those numbers to about 1 to 1.6%. Let's say that about 1% of people who get this disease and get symptoms from it die. That's a non-trivial infection. It's not as bad, of course, as smallpox or cholera or bubonic plague, but it's still not trivial. Furthermore, at this point, we also know, and the mortality depends very sensitively on age, as most people know. So that, for example, if you're in your 20s or younger, you might have a 1 in 3,000 to 1 in 5,000 chance of dying of the condition if you get it. If you're middle-aged, maybe a 1% chance. If you're 75 or 80 or older, maybe a 20 or 25% chance of dying if you get symptomatic COVID. We also know some other things about the pathogen. We know how infectious it is. This is known, as everyone knows now, by the so-called R naught, the R sub zero, the basic reproduction number. That's a measure of the innate capacity of the pathogen to cause new infections in a wholly naturally interacting host that is non-immune. So when the epidemic first starts, what is the intrinsic capacity of the pathogen to infect more people? This number is between 2.5 and 3.5 for this pathogen, probably between 2.6 and 3, let's say 3. So 1% case fatality rate, basic reproduction number of about 3. But this pathogen has some other sneaky qualities we've now also been able to ascertain. One of them is its ability to cause super spreading events. And this can be measured by something known as the dispersion parameter, or kappa, and was beautifully discussed in a paper by Lloyd Smith in 2005 in the journal Nature. And so to get a feel for this, I'd like you to think about the following alternatives. Imagine you have 100 people in a population, and each of them, if infected with SARS-CoV-2, could infect 3 new people. So the R naught would be 3 in that population, but everyone has the same R naught. Now imagine another population of 100 people. 99 of them can infect no one, and 1 of them can infect 300 people. They're like a super spreader. Again, the R naught in that population would be 3. Now, you should have the intuition that in this type of a situation, if a person from the first population migrates and goes to a new location, it will inexorably set into action of the epidemic. They will infect 3 people, and those people will reliably infect 3 people, and so forth and so on, and the epidemic will continue. But so there you have a very small dispersion. Everyone has the same R naught. But in the latter population, you have a high dispersion, and there, if one person moves from this population of 100 somewhere else, 99 out of 100 times, the epidemic will dead end and will not continue. And this is, in fact, one of the qualities of this pathogen. It has this variation in the R naught across people. Many transmission chains are dead ends, but we also have frequent super spreading events. And this has implications for how we manage the condition and for how we discern what's happening. And finally, in terms of the introductory epidemiology, but I could keep going, but I'll just mention one more feature. This pathogen has a very annoying property of affording the opportunity for asymptomatic transmission. That is, the infectious period in an individual, the moment when they are able to transmit the disease, often arises before they themselves have symptoms. Now, this is not always the case. For example, if you think about the disease smallpox, people with smallpox cannot transmit the disease until they develop pustules on their body. So we can use their symptoms to discern who is infected. Conversely, if you think about HIV, people with HIV can be completely unaware that they have the virus and spread it for years before they get symptomatic. SARS-CoV-2 is like HIV. You can spread it before you have symptoms, and this makes it very difficult to manage. In fact, many studies now suggest that up to 75% of cases of SARS-CoV-2 arise from asymptomatic transmission. And before continuing, I want to say one other thing about this pathogen, because it's just dumb luck to us that the pathogen is not worse. There's no God-given or intrinsic reason that this pathogen couldn't be infecting killing 10% of the people who get it, or 30% of the people who get it. We could, in fact, have been facing a worldwide bubonic plague type situation. And many experts have been fearing these types of respiratory pandemics for a long time, and fearing that they would be even worse than what we're facing. So bad as COVID-19 is, I want people to realize it could have been worse. The disease could have been more fatal or more transmissible, or both. And we're just lucky that it is not. Now, as Ido said, my own work in this began in January, and I'll just summarize a few big data projects we're doing because they provide some insights into how you could use data techniques to track and forecast the course of the epidemic. One of the first things we did was, beginning in January, I had some Chinese collaborators that I've been working with for a long time, and we'd been using anonymized Chinese phone data to study a number of social phenomena. For example, when there's an earthquake, how does an earthquake reshape human social interactions? Or if you build a high-speed rail line, how does a high-speed rail line change interactions and therefore prompt economic development? And we were using phone data over large spans of time to study these phenomena. And in January, I was speaking to my colleagues in Hong Kong at the Chinese University of Hong Kong and at Hong Kong University, and some other colleagues from mainland Chinese universities. And we decided that we could use these data to track the course of the epidemic in China. And what we had is we had phone data regarding the physical transits of human beings through Wuhan, which for hundreds of years has been a central transportation hub in China, as luck would have it. We were unlucky that the virus leapt to the human beings in a very large city that also happened to be a transportation hub. And it would be like, well, anyway, I was going to compare Wuhan is like New York City versus the virus, let's say, taking root in Bismarck, in the Dakotas, for example. So it was bad luck for us that it started there. And we had information on 11 million transits through Wuhan up until January the 24th. And we could see these people spread out across the country. And just using the phone data alone, just using information about the movement of human beings, we were able to predict the timing, intensity, and location of the epidemic up through the end of February in China. And we developed a model that allowed this forecasting, which we call the risk source forecasting model. And it can allow you, using human mobility data, to predict the course of an epidemic. But while I was working with my Chinese colleagues doing this, and that was the paper that Ido mentioned that we submitted February the 18th, it was actually quite an exciting moment for me in my career because I hadn't pulled all-nighters since I was in graduate school, but with my collaborators on the other side of the world, we were working 24 hours a day for 3 weeks to get this manuscript completed. But because I was so intimate by then, so aware of what was happening in China, by the end of January, on January the 24th, the Chinese were so concerned by the virus. After initially covering it up and doing a bunch of stupid things, they began to take it very seriously. And they were so concerned about it that they essentially detonated a social nuclear weapon. The Chinese put 930 million people under some form of home confinement, beginning January the 24th through the end of March and into April, which was astonishing. And this really got my attention. And as I was sitting at my desk at the end of January, I could think of no reason why the same thing wouldn't happen to us. There was absolutely no reason the virus would not come to us. And every epidemiological expert I was in contact with at the end of January felt the same way. So I became very concerned, and I began to direct my lab to begin to look at some of these topics. And we began to do a whole bunch of things. One thing we began to do was to look at the, because by the springtime, we had the primaries, the political primaries were taking place. And I was very concerned that turnout to voting, the assembly of people in polling stations, would contribute to the pandemic. And in partnership with Eric Feltham, one of the statistics grad students in my laboratory, we did an analysis of whether turnout to vote on particular days in particular locations throughout the country in the United States affected the trajectory of the pandemic in those counties, at the county level. And to my surprise, we found the answer was no. So when we started the project, I had thought that voting, turning out to vote, was a kind of mass gathering, and that surely could not be a good thing. Although back in the spring, the prevalence of the pathogen was still relatively low in our country. But it turned out that that was not the case. And I think part of the reason was that if you actually think about voting, and since then we've now learned a lot more about the virus and its transmission, people line up outside, for example, before they go inside. When they're inside, they're there for a very brief period. Voting is a private event. You're not face-to-face with other people. You're in a little cubicle. It's quiet. People aren't raising their voices or shouting, as we now know is a mode of transmission. And it's brief. You're inside only for a brief period. So that's another project that we did that we've now posted online, and if you're interested, you can look at. My laboratory also began to work with some of the software engineers in the lab to prepare an app, which we call Hunala, H-U-N-A-L-A, Hunala, H-U-N-A-L-A. This app is available on the Apple Store and on Google Play. It has thousands of users. It is like Waze for coronavirus. This is not a contact tracing app. It's not a backward-looking app. nor is it a citizen science app, which just has people report their symptoms for use by public health authorities. It's an app that users can actually use to forecast their risk of getting the virus by kind of like Waze. In other words, Waze, people are driving down the highway, you're driving down the highway and there's no police stop and there's no traffic jam where you are, but 3 or 4 miles down, people have reported that traffic is at a standstill. You can be notified about this, and then if you wish, you can exit the highway and avoid the traffic jam. That's sort of what our app does. It crowdsources information about the location of the virus, and based on where you are in social networks and where you live, it feeds back to you risk models and estimates of your probability of becoming infected with a virus in the near future. The app, at the beginning, it asks to access your contact list, but we do not copy your contact list, and the app, if you allow it, accesses your contact list just to make it easier for you to signal who you interact with. It does not copy. There's no privacy consideration of that kind. And we began a number of other projects in the lab. As Ido mentioned, I decided to work on this book. And part of the reason for that was back in February and March, I was very concerned that our leaders in this country, beginning at the White House, were trivializing this epidemic. We're not taking it seriously. And I thought that there was a significant need for people to understand what was happening to us epidemiologically and historically, and that led to that other effort. Let me just say a few things more about the what I think is likely to happen in the coming years, and then I'll close with sort of one big idea. It's actually not such a big idea. It's just an idea. So earlier we talked about the R naught, and that for this pathogen it's about 3, and this property, the infectiousness of the property, is mathematically related to what is known as the herd immunity threshold. Herd immunity, as many listeners have probably been thinking about, is the ability of a population of people to be immune to a disease, even if not every individual is personally immune. So imagine, for example, you vaccinate 96% of people in a population for measles, and one of the 4% unvaccinated people gets a case of measles somehow. That person would be very unlikely to be able to start an epidemic because almost everyone they interact with is immune. So you don't have to vaccinate 100% of the people. Just vaccinating 96% of the people is enough to make the whole group of people immune. Well, you should have the intuition that the fraction that you need to vaccinate or that need to acquire immunity naturally is connected to how infectious the disease is. Measles is the most infectious disease known, so the herd immunity threshold is super high. Most of you know that for seasonal flu, nowhere near half or all of Americans get vaccinated every year. In fact, about 30% of Americans is enough. And that's because the R naught for measles, the basic for the flu, for seasonal flu, the basic reproduction number is about 1.5. So to calculate the herd immunity threshold, you use the formula R naught minus 1 divided by R naught. So if you plug in the number 3, which is the basic reproduction number, the R naught for coronavirus, for COVID, you get 3 minus 1 divided by 3, that's 66%. So the herd immunity threshold, using the standard formula for this virus, would be 66%. Now, it turns out that that calculation makes some assumptions, something known as the well-mixed assumption. It assumes that everyone in the population has an equal probability of interacting with or becoming infected by everyone else. That is not true of real-world populations. And network science insights, including a whole bunch of ideas that Ido Aroldi has innovated in, suggest that that number needs to come down. So, in fact, the herd immunity threshold in the United States is probably 40 to 50%. Let's say 45% of people need to be immune in order for us to have herd immunity and reach that threshold. Well, right now, only about 12% of people in the United States have naturally acquired the disease. So we're still at the opening act of this pandemic. We've got a long way to go. We're not at the beginning of the end. We're just at the end of the beginning of this pandemic. And absent a vaccine, which I'll come back to in a moment, this would be the natural course of the virus. It would just spread and spread and spread until it reached the herd immunity threshold. Then the epidemic force of the virus would decline. The virus would still be around, but we wouldn't have this sort of escalating epidemic any longer. So what do I think is going to happen? As we've all seen in the news, vaccines are already in late phase 3 trials, which is just miraculous. Unlike our ancestors for hundreds of years who had no access to any effective treatments, we happen to live at a time when our time in the crucible of this plague, is when we actually can invent effective preventative measures like vaccines. So we've seen 2 so-called RNA vaccine trials release their results, and more vaccines, no doubt, will be released. Most of them will begin, or these trials will begin to be documented, these vaccines as effective, let's say in the first quarter of 2021. But inventing a vaccine and getting its approval is just the first step. Then the vaccine millions of doses must be manufactured, must be distributed, and most importantly, must be accepted by the public. And in my estimation, this will take a substantial amount of time, maybe a year. So that gets us to early 2022, by the time we have vaccinated enough people with whatever vaccines we have available. Meanwhile, the virus is still spreading. So from my desk, 2022 is a moment when either we will have reached herd immunity due to vaccination, or we will have reached herd immunity due to the natural spread of the virus. And at that point, the biological and epidemiological force of the epidemic will now be behind us. But we still need to recover from the psychological, social, and economic impact of the virus. More than 30 million Americans are out of work. Many businesses have gone out of business. People are not going to instantly return to restaurants and airports just because we've reached herd immunity. It's going to take time. People are still going to be wearing masks. There's still going to be physical distancing. And if you look at historical epidemics, that typically takes 1 to 2 years. So I think that intermediate period is going to last till 2024. And then in 2024, the post-pandemic period will begin. Now, usually during times of plague, people, now, people get more religious, for example. People get more abstemious. People stop spending money. People get risk averse. These are all things that we're observing. People get lonely. These are all things we're observing in this pandemic as well. But what will happen in 2024 is that all of those things will now start reversing. People will relentlessly seek out social interactions to nightclubs and restaurants and political rallies and sporting events and mass gatherings. People will start spending money again, I think, quite liberally. There'll be a kind of joie de vivre and risk-taking, maybe some sexual licentiousness. In fact, one person read my description of what was going to happen, one reviewer of my book, and said, here's hoping that that's what will happen in 2024. So I think that is what's likely to unfold for us between now and then. Let me just close with one final set of observations, which is not strictly statistical or forecasting, but just has to do with where I think our country is right now. I think it's very important for people to realize that during a time of epidemic disease, there is no life without risk. Everything you choose to do, everything every firm chooses to do, necessitates weighing risks against each other. Even the 14-day threshold for quarantine is actually, there's a distribution of infectiousness. It's not like by 14 days, 100% of people are no longer infectious. Actually, at 14 days, 2.5% of people are still infectious. So you're taking a risk. Even if you do a 14-day quarantine, there's some small risk that actually that person could still infect you. And you have to judge. Do I send my kids to school? Do I go out shopping? Do I have my college-age kids come home for Thanksgiving, or do I not take that risk? Every single action that we engage in necessarily involves an assessment of risk. And this, therefore, requires us in our society, in my view, to be more honest and more mature about what we're facing. Nobody wants to have to face this serious calamity. But unfortunately, this is the reality of what we live in. And what we are being called for in our country and in all countries is to sacrifice, to service, to honesty, to concern for our neighbors, and for a willingness to work together to combat this virus during our time of plague. Thank you.
Thank you very much, Nicholas, for your very informed and scientific perspective on the topic. I really appreciate it. We're lucky to have you here.